Welcome back. Uh, in this video, I'm gonna prove the theorem uh, of the directional derivative. So, look at the theorems. The first, let's say f be a differentiable at a comma b. So f is the multivariable functions. So graph of f must be the curve, the plane. Second one, vector u be a unit vector in the xy plane. Then directional derivative of f at a comma b in the direction of vector u is, I mean, this one, directional derivative can be computed by dot product of the gradient, which is the vector whose component is consisted of the partial derivative of f with respect to x and y with a unit vector u. Okay, so this one is denoted by that symbol. Read it as gradient of f at a comma b. Okay, so so when you compute the directional derivative of vector u, we gonna find out the gradient of f, which means that find out partial derivative f with respect to x and y, and then we do dot product of that gradient with unit vector. Okay, so how come here? Okay, here's a proof. So here's a strategy. First, we're gonna express function multivariable function f in terms of the only one single variable. Okay, so how can you do that? We're gonna parameterize the two independent variable x and y with a single variable. Okay, so but before doing that, let's just plot the graph of f and then directional derivative and vector u. Okay, so to figure out the what's going on here. So this is the graph of the function, multivariable function f of a comma b. Let's say z equals f of a comma b. Then the graph of function f going to be just curved plane like this. Okay, and then let's say vector u. This is a position vector u. Okay, so for u is right there. Then we draw the equivalent, the position vector. I mean equivalent vector to the position vector u. And here, whose starting point is a comma b. Okay, so now we wanna then that point, the z value of this one must be f of a comma b. Okay, that's just typo. Just f of x comma y. Okay, not a comma b. I'm sorry. It should be. It's gonna be x, and this is y. Okay, sorry. All right, so this is f of a comma b. That's a z value. Okay, so we want to find. Let's say we want to find out the directional derivative of f along that the unit vector u. Okay, so then it means that we want to find the slope of tangent line. Okay, that tangent line. Okay, on along that curve. Okay, so this curve is the intersection of the curved plane with the dot line. You see the line L, which is same direction as the that vector u. Okay, so we'll find the vertical plane containing that line. Okay, we cut the that curved plane with that vertical plane. Then we're gonna get that intersection curve, that curve. Okay, so we'll find the slope of tangent line of that curve at the a comma b comma f of a comma b. Okay, so that's gonna be see that a comma b comma f of a comma b right there. So all right, so so now you see then but let me figure out general expression of the any point on the line. See that? Okay, using the parameterization. Okay, so we can express that point which is on the line L as a plus s times u1 comma b plus s times u2. It makes sense, right? Because and see because s is just what the role of s is the control the length of the vector. Okay, so if s is the positive, then that vector will be elongated in that directions. If s is negative, then the point will be right there. Okay, so yeah, simply we can represent any point on the line L as a plus s times u1 comma b plus s times u2. So now we define then the function g of s as the f of x comma y. Okay, so this should be just x, okay, and the y. So, but we express the x as a plus s times u1 and the y as b plus s times u2. So you see that that multivariate function was what we express this one as a g of just single variable s. By the way, the s, that variable, I mean parameter s, is along the line L, right? It means that along the curve, that curve, right? Because the direction of the curve is exactly same as the direction L, right? And then what g of 0, when parameter s is replaced by 0, then then this is nothing but the value of g of 0 is nothing but f of a comma b, right? So that means that the derivative of g with respect to s is going to be directional derivative f along the vector u, because as s increase, the point x comma y move along L in the direction of vector u, because the line L, direction of L is exactly the same as the direction of the vector u. So it means that g prime of 0 is equal to, because of this and this, g prime 0 is equal to directional derivative of f along the vector u at a comma b. Okay, so now using the chain rule, we can figure out the g prime 0. Then g prime is actually what? G prime is a derivative of f. But f is what? Here, the s and u1, f is the a plus s times u1 and b plus s times u2. So we got to use a chain rule because s is variable and the u1 is also, we can say, the x, actually x is also the function of s. F is a function of x comma y, and the x and y are also a function of s. So we gotta use chain rule. Then the g prime 0 going to be partial derivative f with respect to x, which is a derivative of outer function, and then dx and ds, this is inner function. Okay, plus the outer function with respect to y, right, and then inner function with respect to s. Okay, but dx ds, which is a derivative of x with respect to s, is u1. Okay, the derivative y with respect to s is u2, because I told you, see that here x is x equals a plus s times u1. Okay, so derivative of x with respect to s is what? Just u1, because u1 is a coefficient of s. Okay, so now then the dx ds is u1 and this is u2. Okay, then this one can be expressed as the dot product of the gradient and the vector u. Okay, and then since s equals 0, I see that s equals 0, so the and then there is, the variable in parameter s is not involved in this computation, okay, in this calculation. So that's kind of meaningless. So anyway, so we see that the directional derivative is weighted average of the partial derivative of fx and fy, which means that, see the weight, this we can see this one as weight. Okay, the vector u is weight of the gradient. Simply saying that. Okay, so the that's the interpretation of the directional derivative. So directional derivative in the can be obtained by dot product of the gradient and the vector u, and then we can interpret that as the as the directional derivative is a weighted average of the gradient with a weight vector u. Okay, so that's for today.